Welcome, everyone. We are so very excited to begin tonight's program. We have a really exciting program for you all tonight. Go ahead and take a couple of more seconds, and if you have not voted for our poll, that is, please vote. We've got good participation. We have about 190 people who have voted so far. And so far, in the question of would you rather visit the Earth's moon or black holes, the Earth's moon is indeed winning. But we are very, very excited to get started with the program. As many of you know, 60 Minutes in Space has now gone virtual. So thank you all for making that happen. At the end of tonight's program, we're going to pull questions from the chat for our two fantastic space scientists. So feel free to type your questions as they come up. And we might not be able to get to all of them, but I will do my best to pull as many of them as we can. You might not be able to see each other's questions, but we can, and we will pull the ones that we're able to. To begin tonight's program, I'll keep the poll going. We'll just hide it. But I'll go ahead and hand off the program to Dr. Ka Chun Yu. He is the resident PhD astronomer and curator of space science at the museum. Ka Chun?
All right, thank you very much, Celine. Hello, everyone. Welcome to 60 Minutes in Space. For those of you who are new to this, 60 Minutes is our monthly recap of the most interesting, at least to us, and exciting space science news from the past month. And normally we rotate through space scientists, both internally and with having online programs. We've also been inviting more outside guests to our programs. And for tonight, we have a very special guest, Sachin Shenoy, who comes to us from the Space Science Institute in Boulder, Colorado. And I will do a proper introduction of Sachin right after my story. But he will be talking about this exciting new discovery about the moon that was just announced 2 days ago. So welcome, Sachin. And before we get to it, I just wanted to say, 60 Minutes is, we definitely welcome your questions, and so please put them into the chat, and Celine will go through your questions and ask them of us at the end. So definitely feel free to post your questions during our presentations, and we'll try and address as many of them as possible at the end. But so I've already announced what Sachin's topic will be, or hinted at it. My topic for tonight is actually another big announcement, which came just 3 weeks ago. So on October 6th, the Nobel Committee from the Royal Swedish Academy of Sciences announced that they were awarding the 2020 Nobel Prize in Physics to 3 people: Roger Penrose, Reinhard Genzel, and Andrea Ghez. And all 3 of these scientists were involved in black hole research. Roger Penrose in the 1960s wrote one very key paper that was some people thought was the most important contribution to general relativity since Einstein. And so I'll talk about his work. And then finally, Reinhard Genzel and Andrea Ghez both led 2 independent teams, one in Germany and one in the United States, who starting in the early 1990s, they started to observe the Galactic Center. And so they were the ones who provided the best evidence that our own galaxy has a supermassive black hole at its center. Now, for black holes, in order to understand them, black holes have appeared in popular literature. They've appeared in movies and in fiction. But in order to really understand them tonight, we have to go back to the basic physics behind them. And that is Albert Einstein and his general theory of relativity. So over 100 years ago, Einstein came up with both his special theory of relativity as well as his general. And often, these are very complicated topics to try and explain. So I'm going to try and explain it in 2 minutes. And so basically, the very first thing that you have to understand about relativity is that Einstein came up with this idea of space-time. So normally, for us in our ordinary lives, we think of space and time as being these two very different concepts in the universe. Space is sort of like the realm in which events can happen, and time is sort of a way of ordering these events as they're occurring in the universe. But what Einstein realized was that space and time couldn't actually be separated. They were actually two components of the same thing, which he called space-time. And so space-time was this four-dimensional construct that included the 3 dimensions of space that we're familiar with, as well as the dimension of time. So that was something that he realized well, these are both concepts that he realized in special relativity. The second concept is the idea that mass and energy are equivalent. So he realized that energy and matter are basically 2 halves of the same coin, that you can turn one into the other. And the way you do that, the way that they're equivalent is through his very famous equation, perhaps the most famous in all of science. Energy is equal to mass times c squared, where c is the speed of light. And so that tells you how much energy you get if you were to convert all of some matter into energy. And then the kind of the brilliant realization that he made in general relativity was to combine these two concepts, the idea of space-time as well as matter and energy. And he combined them by showing how space-time could be warped or altered by matter and energy. And as a consequence, that warpage or the change in the geometry of space-time would alter or affect how matter and energy propagated or moved through space-time. And so the two basically affected each other in ways that people hadn't realized before. And so basically, matter and energy tell space-time how to curve, and then the curved space-time, the warped space-time, tells matter and energy how to move. And Einstein conceptualized these two effects through his field equation, which looks really simple, but it's actually a complicated set of actually 16 equations. And on the left-hand side, that G represents how space-time is curved. And then the right-hand side tells you the matter and energy that is responsible for that curvature. And so we're not going to go deep into any mathematics tonight, but often people have tried to visualize what this means. And because you're dealing with 4-dimensional mathematics, that's not, there's no easy way to visualize it. But one way that we've tried to do it in our Black Holes, the Other Side of Infinity planetarium show, is to represent space-time as this grid. And you can see with the sun, the grid gets distorted because of the mass of the sun. And oftentimes you'll see that distortion not in a 3D grid, but in a flat plane, like a big rubber sheet. And so you can see that distortion again for the center of the sun. And then that you also see a smaller distortion due to an asteroid or a body that's in orbit around the sun. And that body is in motion because of the distortion of space-time caused by the larger body. Now, only a month after Einstein came up with his general theory of relativity, Carl Schwarzschild came up with a solution to his equations, where he basically used the equation and found to describe a spherical object with a certain mass m and a certain radius r. And it turns out that this equation describes the simplest type of black holes that we can possibly describe. Now, people didn't do much with this with regards to black holes until about 20 years later, when Robert Oppenheimer and his student Hartland Snyder worked on this problem, and they took Einstein's equations and they tried to use it to describe what would happen with a cloud of matter that was collapsing inwards down to a point. And they even realized that this would be an object whose gravity could become so strong that it could slow down the propagation of light, so much so that it could keep light from reaching the external universe. And so this is the first real description of what a black hole might be like. But their ideas were actually met with a lot of skepticism, if only because other physicists thought that because they relied on a perfectly spherical object collapsing, and people thought a perfectly spherical object couldn't possibly exist in the real world, in the real universe. And if something wasn't exactly spherical and it wasn't a perfect sphere, if it collapsed, there was no guarantee that that object would end up colliding at the center to create this proto black hole. So we had to wait until the 1960s to get to Roger Penrose, who is the first Nobel laureate that we're talking about. And Penrose was actually a mathematician, so he didn't actually have any physics background, but he heard a lecture on Einstein's theory of relativity and the Schwarzschild metric, that solution to Einstein's equations. And so he became interested in this topic, and so he taught himself physics, and he also talked to other people, to actual astrophysicists, astronomers, to learn more about astronomy and physics. And at Oxford, where he's been, well, he started working on this before he got to Oxford, but he came up in 1964 with a new mathematical description of relativity. And this was a little bit more general. So it was still about a collapsing object, but it didn't have to be perfectly spherical. So it could deviate from a sphere. But he basically showed that a black hole could be a real thing in our universe and not just some theoretical idea. And so this is the diagram from his paper, which is really complicated, but it shows what's known as nowadays known as a Penrose diagram. And basically, this is a diagram that Roger Penrose invented to show graphically how space-time would work within the framework of any particular solution to Einstein's equations. And so here is a simplified version of his Penrose diagram. And the way Penrose diagrams work is that they collapse the dimensions of space and time into what you can draw on a sheet of paper. And so the dimensions of time is along the vertical axis. So at the bottom is earlier, it's in the past, and the top of the diagram is in the future. So if we're watching something happen, that something would move from the top to from the bottom to the top of the diagram. And what this diagram shows is the collapse of a star. So that star is represented by that kind of that reddish pinkish cone. And so the star is actually a flat 2D circle, but since we're seeing it move through the dimension of time, it shows up as this cone. And so the star gets smaller and it collapses, and that black cone basically represents the event horizon for that collapsed star. So that's the point in which nothing can escape from this black hole. And that blue line represents the very center of that collapse point, the singularity. And in addition to that, there are also these light cones, these yellow cones, which represent how light rays propagate into the future. And so light rays will propagate along the sides of those cones along a 45-degree angle, and everything else moving slower than the speed of light will propagate inside those cones inside 45 degrees. And if you look closely, you'll see a few cones that are on the event horizon. And so they show that if you happen to fall onto the event horizon, even things moving at the speed of light, which is along the surfaces of those cones, they can only move along the event horizon. They can't escape it. And then for things that fall inside the event horizon, Now, those cones point inwards towards the singularity. So what Roger Penrose basically showed was that from his kind of novel analysis of Einstein's equations using his background as a mathematician, he showed that objects, their trajectories inside a black hole would inevitably point them into the singularity, showing that there was really no escape once you went past the event horizon. So Penrose's work coming in the 1960s really established black holes as this potential thing in our universe. And also at about that time, in the late 50s and early 60s, astronomers started discovering these ultra bright objects in the sky that they called quasars. And they soon realized that these were very distant objects, meaning they were well outside of our galaxy. So here's a picture of a really famous one, 3C273. Because they were so far away, they also turned out to be extremely luminous. So the brightnesses of some of these quasars were 1,000 times more brighter than all the light from our own Milky Way galaxy. And they put out lots of radio emissions, and the radiation also varied on very quick timescales. And it was very difficult for astronomers to explain how these objects could put out so much energy and could vary so quickly. And it turned out that black holes were a solution, that if you had black holes at the centers of galaxies, they could, or at least stuff that was falling in to them via an accretion disk, could potentially pump out enough energy to explain quasars and other type of phenomenon like the so-called active galactic nuclei. And so black holes became really popular as an explanation for things outside of our own galaxy. And people started wondering whether black holes might exist at the centers of all galaxies, including our own galaxy, the Milky Way. And if you look at the Milky Way in visible light, like shown here, there is a bright region, and that's just because the density of stars increases as we go towards the center of our galaxy. But there's a lot of gas and dust that blocks our line of sight, so we don't really see much directly at the center. But if we look at the radio as well as the X-rays, we do see evidence of a bright source at the very center of our galaxy. And so there was a lot of speculation that perhaps the Milky Way also had a supermassive black hole at its center, just like other galaxies. But it wasn't as active, and definitely didn't put out as much radio and other energy as other sources that we saw elsewhere in the universe. So perhaps this was a smaller black hole, or one that wasn't ingesting as much material. So as a result, astronomers have been observing and making careful observations of our galactic center for many decades, and they've discovered the galactic center is this extremely dense, extremely complicated region with lots and lots of stars, lots of gas clouds and dust clouds, and it's a very dynamic region. But because it's about 26,000 light years away from us, that's how far the sun orbits around the center of the galaxy, there's lots of obscuring gas and dust that prevents us from easily making observations of the galactic center. And so what astronomers had to do was they had to observe, instead of in optical light, the visible light that our eyes are sensitive to, they had to observe in the infrared. And the infrared allows you to pierce through much of the gas and dust. And in fact, Sachin will be talking more about infrared observations, because that's the telescope that he'll be talking about is done, all of its observations are in the infrared. But when you look at the galactic center in the infrared, you see hundreds of very bright stars. These are extremely massive stars packed in there. The density in the galactic center is about 1 million times denser with stars than it is in our own solar neighborhood. And so if you were to go and visit the galactic center, you would have this amazing view of millions of times more stars, but also the stars because many of them are supermassive, they can be hundreds of thousands of times brighter than the stars that are around us in our galactic neighborhood. Now, one of the problems with observing any star from the Earth, from a ground-based telescope, is atmospheric turbulence. So here is a series of images of observations of one star. This is a negative, these are negative, so black means bright light, and the white is actually the absence of light. And so these are very quick frames that were taken, and this is of one star. So normally you think of one star with all of its light packed into one location in the image, but you can see that the star actually jumps around. And not only does it jump around due to the turbulence in the atmosphere, but the single point of starlight actually even breaks up into multiple points. And you can see that the locations of these points, the number of these points, and how bright they are, the astronomers call these points speckles, they change pretty randomly just because the turbulence in our atmosphere is pretty random. Here is another view of the speckle, not from one star, but from a binary pair of stars. And so you can see a very complicated pattern of speckles, of those points of light. And normally what astronomers would do is they would let their detector sit on this spot in the sky for multiple, perhaps minutes or hours, in order to get enough information, just because many of our sources are very faint. But what would happen is that if you're imaging lots of these speckles that are very random, is that you would get a result that sort of looks like this, where all the speckles kind of add up into just one low resolution blob, whereas what you're trying to get is this, which is the image of the two the pair of binary stars. And in the 1970s, astronomers realized that you could actually mathematically go back. If you took lots of images, let's say thousands of images, all within a split second, you can actually go back and reconstruct the original image of what it should look like from your sub images. And so with that, you can have an image of, and today we can create images like this, where the planet Jupiter looks blurry on the left, but with the speckle reconstruction, you can get a much sharper view. And this is where we can return to the story of Reinhard Genzo and Andrea Ghez, who in the early to mid 1990s, they started to observe the Galactic Center. Both of them were interested in possibly discovering the potential black hole that was there. Genzo led a team at the Max Planck Institute for Extraterrestrial Physics at Garching, Germany. And Andrea Ghez led a team at UCLA, where she was a professor in astrophysics. And both of these teams have been monitoring the Galactic Center for well over 25 years. The first results came in 1998, when Genzo's group started getting results from their speckle imaging work. So back then, the Galactic Center was extraordinarily difficult to observe. It still is. So they had to use the speckle imaging to try and get high resolution images of the Galactic Center. And in 1998, they released data from 2 years worth of observations between 2014 and 2016. And they could actually map some of the stars moving. And between those 2 years, they showed that these stars are moving up to about 1,500 kilometers per second, which is over 3 million miles per hour. And what they showed was that this was consistent with a supermassive black hole at its center with a mass of at least 2 million solar masses. And note here that what they're seeing are the stars in orbit around this supermassive black hole. They actually don't see, at least in the infrared, any evidence for the black hole. And then around the 1990s, another technique called adaptive optics became important in astronomy. And this is similar to speckle imaging in the sense that you're trying to correct for the turbulence in the atmosphere, but you're actually doing it on the fly. So instead of collecting all the images as the star is jumping around, you actually correct for the jumping of the star so that you get a stable image of the star. And so both teams, both the Genzo team and the GES team, did that at their respective telescopes. The very large telescope down in Chile for the Europeans, and the Keck telescope in Hawaii for the Americans. And in 2002, they started releasing the results. So both teams were competitive, and they started seeing very similar results. Genzo's group, for instance, measured the star which he called S2, rounding the galactic center, and that's that elliptical orbit that you see on the left. And they was moving up to about 5,000 kilometers per second at its very closest point to the galactic center, around, again, this dark source, which was bright and radial, but wasn't visible at optical wavelengths or in the infrared. And they were estimating that this was a black hole of at least 3.7 million solar masses. Andrea Ghez's group came up with a similar number, about 3 million solar masses. And here is an animation of the data from Ghez's group. So it started in 1995, and it goes up to until last year. And that yellow orbit, that innermost orbit, is that S2 star or S02 star. And that's the star that is moving the fastest. And because its orbit is only 16 years, it was the one star that they could actually see or observe through an entire orbit. And then finally, here is an animation from Genzo's, from the European Southern Observatory, that flies us into the galactic center, and we'll see the orbits in this 3D simulation. So as we're flying through this, I want to just close with a highlight, a number of highlights or conclusions about these discoveries. First of all, astronomy, like many other sciences, requires parallel efforts from theorists as well as observers. So you need the people, the theoreticians, looking at the theory, making predictions, explaining to us what might be possible, or trying to explain what might be happening in the universe. But of course, the theory is nothing without observers confirming the theoretical predictions, because oftentimes theorists can come up with lots of crazy and wild ideas, some of which don't pan out. And so you really do need to have observers who can ground the theory in the truth of observations. And then finally, I think this story also shows how difficult science can be, and that it can take a really long time for scientists to get results. People can often spend many decades of their lives working on a single project, collecting data that can be extraordinarily difficult to collect. I mean, if it was easy, people would have done it a long time ago. So the fact that it took many decades shows you how difficult it was. And both Genzo and Gez had to deal with their skeptical peers. When they started their projects, other scientists were saying, yeah, this was impossible, just because they didn't think telescopes could accurately observe the stars at the center of the Milky Way. And in fact, they had to create their own techniques, as well as rely on new technologies in order to make the observations that enabled their discoveries. So this really shows that persistence in science is really important. All right, so with that, I want to introduce Sachin Shenoy, who, as I said, is he's an astronomer and scientist with the Space Science Institute in Boulder. He has been working with the SOFIA mission for well over, is it 10 years, 8 years or 10 years? He'll correct me if I'm wrong. But he was based in the Bay Area for many years, but just 2 years ago, he moved to Boulder and is working remotely with the SOFIA mission. And so he's going to be talking to us tonight about that mission, as well as this major discovery of water on the moon. Take it, Sachin.
Thanks, Ka Chun. Appreciate that. Yeah, I was working for about 8 years with Sophia, and now I'm living in Boulder, Colorado. This would be a bit difficult topic for me to talk about here. Not topic for it, just the format that I don't see any of my audience, and I'm one of those speakers who looks at the audience, gauge their reaction, and interact with them. So this is hard for me. So forgive me for that. But let's get on with it. So last week, if you were looking at news, you'd start seeing things like this. NASA to announce an exciting new discovery about moon on Monday. NASA to announce exciting new discovery about the moon made by the Airborne Observatory. And this was coming all over the place. Places like Earth and Sky magazine, or USA Today, or even Independent in Britain. So what's all this hoopla about? So this has to do with a paper that we recently published. It's really recent. It was published on Monday by Casey Honeyball and Paul Lucy, where they mentioned that, yes, water has been seen by 3 different spacecraft on the surface of the moon, a particular feature of water called 3 micron. We'll go into details in a little bit. But what we discover is this: we discovered a different vibrational signature of water at 6 micron. And it was done by this thing called Sophia. So today I want to talk to you about how we went about from knowing there was some water on moon, or there were indications that there was water on moon, to detecting this 6 micron feature. And I talk about how these features come about, what instruments we used. So there's a lot of background I'll be giving. So, and I do know there are some experts in the field. So you guys can go to bed now. And when I talk about science, the last 10 slides, I'll wake you up. All right, so let's start with Sophia. What is Sophia? So Sophia stands for Stratospheric Observatory for Infrared Astronomy. It's a 747 plane. It's a 747 SP for aficionados. What that means, it's a bit shorter than a regular 747 plane. It has a more powerful engine, and the fuel capacity is much higher. What these allows the plane to do is it allows the plane to fly much higher than normal 747, and it also can stay in air for a longer time. So this mission has been funded by 2 institutes. NASA, 80% of the funding comes from NASA and 20% from our German partners, DLR. And the plane looks something like this. And we usually, every night when we observe, we fly up to 40,000 feet. We open up the side of the plane. And when I say we open up the side of the plane, that's really a big opening. It is 15 feet by 22 feet. So you can sort of drive a truck through it. And inside there is a 2.5 meter telescope, about 100-inch telescope. That's the telescope sitting in the between. The telescope weighs about 20 tons, and we do our observations. If you look at a cutout of the plane, this is how it looks like. In the back here is the telescope, 20-ton telescope. The right light reflects off a couple of mirrors and then comes into this tube. And here is where the black tube that you are seeing, that is where the instruments are mounted. Then there are the computer racks sitting here, which controls the telescopes and the instrument, and the computers are controlled by all these independent guys sitting here. We do have guest observers sometimes fly with us, and they get to sit in the first class. So as you can see, this is not like a regular plane that you fly on. When you go inside, this is what it looks like. It gets pretty crowded in there. So there is the telescope with the instrument sitting up here. These are the telescope operators. These guys standing and sitting here are the instrument operators. We have mission director sitting here. She or he will be the one who will coordinate the entire flight and make sure everything works smoothly. One of the questions I keep getting is that you're flying at 0.8, 0.9 Mach. How do you keep the star at the center? And when you're standing inside, it looks something like this, as if the telescope is moving all over the place. But in reality, it's not the telescope that is moving all over the place. It's the plane that is moving all over the place. So we are having turbulences and the plane is moving, but the telescope is in its own inertial system. And that is achieved by 3 technological ideas. The one is we have pressure dampers here. You don't see it, but there are the black pressure dampers, which removes the 0th order vibrations. The second one is this whole thing around here is a gigantic bearing, and we flood the bearing with oil when we reach about 10,000 feet, which means the entire telescope gets lifted off the plane, and now the telescope is independent of the plane. The last thing is we have 3 gyroscopes, which when we looked at the star and track on the star, it makes sure that the telescope stays stable regardless of what happens to the plane. So now, as the name suggests, SOFIA is an infrared telescope. So we look at the infrared. Most of you are used to looking at visible images. So if I look at a galaxy in the visible, this is how it looks like. But in the last few decades, we have managed to look at our universe throughout the entire electromagnetic radiation. So all the way from X-ray to radios. Some of these, like X-rays and ultraviolet, you cannot do it from Earth. You have to go to space, whereas some of the infrared and radio can be done from Earth. So why is it important? Infrared, as you know, is just measuring the heat content of an object. So if you look at this image and you're looking now in the visible light, this is what it will look like. Some people who have very sharp eye will pick out something, which I didn't when I first looked at it. But when I look at the same image in the infrared, this is what I see. And in the infrared, you can pick out the warm objects. And in this case, the warm objects happen to be the deers that are standing on top of this meadow. So there it is. The same thing or the same technique can be used to look at space. So this is the classic Orion Constellation. And I've drawn those lines to draw your eyes to the shape of the constellation. This is a visible image. But if you want to look at it in the infrared, this is what it looks like. The whole constellation glows up now, because now we are looking at the dust and cold clouds that makes this whole system. And all these yellow blobs that you are seeing are the regions of star formation where newly formed stars are being born. So that's what SOFIA does. SOFIA looks at our universe in the infrared. How do we do that? Why do it with SOFIA, and why go up in a plane? What's the big deal? So here I'll have to explain this. Forget about the background image. It's just an image of a galaxy, but look at this blue lines. This is called a transmission spectra. What this is if I have 100% of light, let's say at wavelength 1 micron, I'm getting 100% of the light outside the Earth atmosphere. And if I am inside and watching that light, how much will it get to me? So in this plot, 1 means almost everything that is outside our atmosphere will penetrate through the atmosphere and reach our telescopes and we can see it. If it is 0, that means we don't see anything. So the way to read this plot is this. If you stand on top of Mauna Kea, that's where all the big telescopes are, which is at 14,000 feet on a mountain in Hawaii, known as Mauna Kea. If you stand there and you're looking at around 1.5 micron, almost all the light that is out there gets in through our atmosphere, so we can see it very well. But if you go to about 8 micron, then very little get in. In fact, if you go to about 100 microns, you don't see anything at all. Because the light that is coming from space, once it hits our atmosphere, the molecules and atoms that make our atmosphere absorb this light, so it diminishes the light. So the higher you go, the better it is. Now, SOFIA flies at about 40,000 feet. So when you're flying at 40,000 feet, most of this infrared wavelength is now accessible to us. And in the near infrared, you see almost everything perfectly. At 100 micron, it's not 100%, but still about 60 to 80% of the light gets in. So this allows us to look at really faint objects and get rid of Earth's atmosphere, the signatures of Earth's atmosphere. That's the advantage of going up in the stratosphere. And that's also the reason why, till now, people were building observatories very high up on the mountaintop, because they wanted to get away from most of the water and ozone that's in our atmosphere. So just a basic, really basic idea about spectroscopy, because that's how we detect different objects in space. So imagine you have some light source. This could be a star, a sun, galaxy, whatever. The instrument is built in such a way that the light enters through a slit. You can think of this as a metal plate with a rectangular slit in between. The light enters in and gets reflected, and it gets reflected by a grating. It could be a grating or a prism. And the property of this object is that it splits a single light into its component wavelengths. So you start seeing different colors, basically means different wavelength. When you take this different wavelength and put it on a CCD, you get an image of this slit. And that's how you look at the spectra. This is very basics. The spectrograph that we have is much more complicated, but all those things sit inside this red instrument called forecast. And since we are looking at the infrared radiation, which is basically heat signatures from the universe, which is very faint, we have to make sure that our instruments are very cool. So all these silver things that you're seeing are places where we can put in liquid helium or liquid nitrogen to keep the instrument cool as possible, so that we don't have any signatures from the instrument itself. All right, so how do we detect water? So in the infrared, water has a couple of what astronomers call, or physicists call, transitions. So as you know, water is made up of one oxygen atom and two hydrogen atoms. And these, when they get warmed up, they can start doing this different motions. So this motion is called asymmetric stretch, and it radiates at infrared wavelength of 2.6 microns. The second one in the center is a symmetric stretch, and that one radiates at 2.7 microns. But note that this is an OH or an OH symmetric or asymmetric stretch, which means even if I don't have one of these hydrogen molecules, I'll still see these signatures. On the other hand, if the hydrogen atom starts moving in this scissor motion, then that is called hydrogen-oxygen-hydrogen bending mode, and that is observed at 6.2 micron. And that's the one that we have observed. So the big deal about observing this on Moon was there were a lot of other instruments before this where they have observed these first two transitions. But you can't be 100% sure that this transition is coming from water, because OH can be in other molecules and other compounds too. But this is uniquely, the 6.2 micron uniquely detects water. So here is what we did. This was done as a test case. We didn't know if this was working or not. Moon is a big object and it is extremely bright. So it's really hard for Sophia to see it and guide on the Moon because it's such a big object in our telescope. What we wanted to do was to figure out if there is any water in this region. This is the Clavius crater. If you guys know, this is the Tycho, this is Clavius crater. This is like the mid-latitude, and we put a slit, just like how I showed you in that diagram, we put a slit of forecast on this, and it went a little bit beyond the edge of the Moon to the sky. And then as a comparison, we put some slits here where the hope was we would find some water here, but we need to subtract out all the other effects. And to make sure we know what those other effects were, we put slits here in the Mare region where we expected that there won't be a lot of water, or there will not be any water. Remember that the sunlight hits the surface of the Moon and comes to us. So there is signature of not only the reflected light from the Moon, there will be signature of the water, there will be signature of the Earth's atmosphere, and there will be signature of the instrument itself. So we need to carefully remove out all these features before we can start looking at the water feature. So if you look at one of our spectral images, this is what it looks like. And it's basically the slit image that you are basically stacking up. So the x-axis here is wavelength, and the y-axis is basically the Moon. If you notice up here, we put the Clavius region so that some of it was beyond the edge of the Moon. That's what you're seeing here. That is the edge of the Moon. and this is looking at the background sky. So when you put a slit, the light comes into the slit and gets split up into different wavelengths. So you can think of this as stacking different slits at different wavelengths. So you start at 5 micron and then you keep stacking slits and you're looking at the moon. So here in my x-axis is the wavelength, and this is the location of the moon, different places on the moon, looking at different craters, so on and so forth. Now, how do we extract the data? So if you can extract the data by, let's say I want to extract the data of this region of the moon. So I take a rectangular box and I add up all the signal here, and then my x-axis will be again wavelength, and the intensity that comes out of this box will be my flux. And that's how it looks like. And you don't have to have just in any, you can pick up any region you want, whichever region is interesting to you. It doesn't have to be the same size. You can pick up any different sizes you want. It really depends on what science you are doing and what you are extracting. So when you extract a spectra, this is what it looks like. This is the spectrum of the reference region. And you'll notice that there is a lot of these jagged things. This is due to the instrument. The instrument is not perfect. And when you look at some very faint object, you'll see these jagged things. So we wanted to get rid of this. So we did what a normal astronomer does, that they fit a continuum. The red line is the continuum. You divide the spectrum by the red line and you get this residual. So this is the signature of the instrument itself. Once you take your Clavius region and subtract out this instrument features, what you get is a clean spectrum. You'll see that here there are a lot of these bright bands on the left-hand side, but on the right-hand side, it's all clean. So this is coming purely from the moon and not from my instrument or from my atmosphere. The other way to look at it is here. The black line in this spectrum, the leftmost spectrum, is the data with those instrumental oscillations. Once I characterize that oscillation and remove them out, then what I get is a black line. Here is what the spectrum looks like. And if you'll notice, there's a small bump here at 6 micron. That is my 6 micron peak. That is the water feature that we were trying to detect. And you'll notice that some of the features in oscillations here are bigger than the water feature. So it was really important that we characterize this oscillation extremely carefully and remove that off so that we can find the water feature. So again, we fit a continuum here to get data like this, and we can see the water feature very clearly in this. So we looked at 6 different regions of Clavius, and almost in every region that we saw, we found this 6 micron water feature. The black line here is, remember this, we can look at different parts, different regions of the slit, different parts of the moon. So this black line here is the spectrum that is taken at this coordinates on the moon, and the red one is the coordinate on top here. So the black is the minimum water you will find at, say, 65.3 micron. And if you go to 55.4 micron, this is the maximum you will find. So what does this mean? What are all these results? So the results we have is we have 6 observations of the moon and Mare, and all the Clavius observations show the 6 micron feature. Based on this feature, we can calculate things like how much water is there in the region that we are observing. And we estimate it to be about 1,000 to 400 parts per million. We also see that because we can, because we can look at different regions of the moon, we can figure out how the abundances change as we go to different regions of the moon. So you can see the water abundance and brightness temperature is consistent with what was observed before. What does all this mean? This means that, first of all, distribution of water in the small region that we studied is a result of local geology and not a global phenomenon. That's because we don't exactly know what is happening on the global scale. But the small, tiny region that we observed, we could clearly see water. So how did the water come about there? So there are 2 ideas here. One is that water is created on the surface of the moon, and the other is from micrometeorite impacts. And the way it works is that if I have an OH molecule on the surface of the moon, the sun provides a hydrogen wind, which can come interact with the OH molecule. And then this H2O molecule, the water molecule, can come off the surface of the moon and be in just above the surface. So the result is some of this will be lost to space and some of this will fall back onto the surface of the moon. So you can have some water on the moon created on the surface itself. The other way you can do is you can do it by micrometeorite impact. These are tiny meteorite left over from passage of comets and asteroids, and when they hit moon, they generate a lot of energy. This energy can be used to bond a OH molecule with a hydrogen atom and make water. But our observation does not distinguish between these two. So we can't really tell which of these is happening. Both may be happening, or one may be happening, or one may be important than the other. So we don't know about that. But the one thing we know is that water cannot survive on the surface of the moon just by itself because of the day-night changes in temperature. At daytime, it gets really warm and the water gets destroyed. So you cannot have, so water has to be somehow secluded, somehow kept safe. So there are two ways you can keep water safe on Mars, and one is by in the glass beads. That is, when a micrometeorite impacts the surface of the moon, it creates, from the silicon dust that's up, it creates glass beads, and these beads can capture whatever little atmosphere is there on moon and water that you have in that atmosphere. The other way to do it, you can create voids in the grains of the sand on the surface of the moon and keep it. But because of, again, the day-night cycle, we don't believe that these water that we have detected are in these grains, but it is more like they are in the glass beads. All right, so that's the story about water on moon. And the big deal about this is the first time we have seen a 6-micron feature. So for us as scientists, that's very exciting. And the second thing is we have seen it in a region which is at a much higher latitude, at 55 degrees and 60 degrees, where we were not expecting to see water. So those two were the big deals about this. That's why I think why so many people are interested in this study. And with that, I stop here and I'll start taking questions. Thank you.
Thank you all so much. So we do have about 8 minutes for questions. We will, don't worry, I will not cut you off at exactly 8 p.m. I'll let you finish your sentences. We have some really great questions in the chat. Sachin, we'll start with you. Some folks are just wondering about the logistics of SOFIA. So what does it look like to have the side door open while it's flying? Why aren't the scientists wearing oxygen? So various questions related to that. So if you could just go over that, that would be great.
Maybe I can show it. No, that's yeah, like when SOFIA was first designed, we forget, no one knew what would happen. I mean, every one of us have seen a Hollywood movie where, you know, Bruce Willis comes in and shoots a tiny hole in the window and the entire plane explodes up. But because we have a pressure barrier, we have a pressure between the telescope and the people who sit inside the plane, we are still safe. We still feel like flying in a plane, whereas behind that pressure door, the pressure bulkhead, that's what is open to space. When we did our first flight in like 8 years ago, when the first open door was done, our pilots were very scared to see what happens when this gigantic door opens up. But now when I speak to them, they say the plane is built so well that when the door opens, they don't even realize it's open. For them, it just doesn't matter. They just keep flying. So there are quite a few technologies that we have used to do that. And let me see if I can show you quickly what I mean by that.
That is fascinating. That's also where my brain went to it. It was the
But if you
like
notice,
light.
yeah, sorry. If you notice, there's the small dots all around the telescope. Those are the small hair-like structures. You'll see the small hair-like structures. So
You have to share your screen, Sachin.
Pardon me?
You have to share your screen. We don't see anything right now.
Oh, I'm off. Okay, sorry. All right. You see that now?
Yeah.
So around the telescope opening, there is this small hair-like structure which breaks up the airflow on top of it. If you let an airflow and there is a hole behind the airflow, the air has a tendency of going down into the hole. So what these small fingers do is they break all these eddies and make it a planar flow. The other thing you will notice is in front here, there is a baffle. As I said, when you are looking at the air flowing in, it tries to flow into the telescope cavity, but because there is a baffle, it gets reflected off and goes off again. So that's one reason why our plane just doesn't go up and down, because of this motion of air across things, because the air is very planar. It doesn't have a lot of eddies and it doesn't go inside the cavity. Does that make sense?
It does. That's fascinating. I'm gonna stop your screen share really quick. Thank you. All right, so the next few questions are a little more technical, so I'm preparing you both for that. Ka Chun, we'll start with you. So could you compare the behavior of SMBH with a more energetic star like M87? And also, if I'm looking down, it's because I have my handy dandy super cool technology over here.
Yeah, so the question is about the supermassive black hole. That's what SMBH is in our galaxy versus the supermassive black hole in M87, which is a giant elliptical galaxy that's about 50 million light years away. So this is a much larger galaxy with a much larger supermassive black hole. So the supermassive black hole in M87 is let's see, I actually had to look this up, but it's about 7 billion solar masses in size. So it's much, 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 much bigger than our supermassive black hole. In fact, it's about 2,000 times larger than our 4 million mass solar mass supermassive black hole in our galaxy. And so there, that's actually a big mystery. I mean, part of the mystery of supermassive black holes that astronomers are still trying to puzzle out how those massive black holes can get so big. I mean, you know, we think 4 million solar masses is pretty big, but when you talk about billions of solar masses, that's even bigger. And then the other thing about the M87 supermassive black hole is that that was the one that was imaged by the Event Horizon Telescope project from that you might have heard about recently, when everyone was talking about the image of the black hole, and and because it's 2,000 times larger, the event horizon of that black hole is about 2,000 times the size of our supermassive black hole, but M87 is also about 2,000 times further away than the 26,000 light years that our supermassive black hole is from us. And so people are currently working on trying to do the same thing of imaging our supermassive black hole. And currently the rumor is that they have all the data. And so it's just a matter of time of crunching through those numbers to generate that image. Great question.
Wonderful. All right, so we have time for about one more question for each of you. Sachin, I'll give you one that's been asked a few different times in the chat, which is in terms of the placement of where we're seeing that water on those images in the moon. Is it concentrated in one particular area? Is there any particular reason for that? There's various versions of that question in the chat.
We don't know. We don't know exactly. All we can do is we can look at where our slits were placed. So there is a small region of space on the moon which was sampled by us. And in that region, it looks like it varies. It varies. Some place it's very low, like 100 parts per million. Some places it's a little bit higher at 400 parts per million. So relatively, these are all tiny amounts of water in just that small region. We don't know how the water is distributed at the rest of the moon. We have put in proposal again for Sophia to do a big survey so that we can look at a lot of different regions and compare them. And remember, this is a dynamic thing, right? Water gets created and destroyed on the moon all the time as the day-night cycle changes. So we also want to do an observation during different parts of the lunar day. So yeah, that's all I can say for now.
And I think that goes to Ka Chun's earlier comment about the combination of theory and observations, right? It's not from one day to another. It takes some time. All right. So one last question for Ka Chun.
Yeah, this is just the first observation, such observation. So we have to wait for more observation of these kinds to say concretely how much water is there, where it is, how it is distributed, so on and so forth.
Thank you. So Ka Chun, I won't give you a hardball question. I'll just ask, is there anything that you want to leave the audience with regarding black holes? Some folks are asking, is this like this in other galaxies? I'll let you interpret those questions.
Well, it's kind of a broad question, but yeah, I mean, we have good evidence that black holes, supermassive black holes, are at the centers of basically every galaxy that we've been able to observe carefully. And so I think people can now conclude that supermassive black holes are a part of galactic evolution. And as far as how they end up that way and how each galaxy manages to get the supermassive black hole that it has, whether it's a billion solar mass one or a million solar mass one, that's still a big question. And I think astronomers will continue to investigate black holes in our as well as other galaxies.
Sachin, same question. Any final parting thoughts before we say goodbye?
No, this has been exciting, and I hope you guys see why it excites us astronomers to find these small 1 molecule of water on moon or in a glass bead. So this has been an exciting project that we have been working on for the past year and a half. And I hope, just please support us. Go to our Facebook, Twitter page and keep up with what Sophia is doing. Sophia does a lot of different things. And unfortunately, we don't have a lot of time, but there are lots of questions coming about Sophia on the chat, which I cannot answer. But what you can do is I'll put up my email here. It is just shenoy@spacescience.org. Please go ahead and send me emails with your question, and I'll try to answer all the questions you have. Sorry, because of the time constraint, I can't answer all the questions here. Thank you.
Thank you so much. Wonderful. Well, thank you everybody for joining us tonight. I will also put in the chat our next 60 Minutes in Space is November 18th. We hope that you will join us for that. You can go ahead and register now. But thank you all. We know the world is very hectic right now, so we appreciate you taking some time and looking above our world. We hope to see you all next time.
Thanks, everyone.
Thanks, everyone. Good night.
Good night.